Hi everyone. Hello everyone. Thank you so much for joining this webinar today. My name is Allie Yamagata from Saint-Gobain of America and from the YPN Cement Division Liaison, and I'll be the host for today's webinar. Before we start, I'm going to quickly talk about ACerS and the benefits of being a member. Being a member of ACerS gives you access to resources to allow you to continue to learn and grow. And gain recognition with awards, scholarships, apply to support, travel, and attend conferences. One of my favorite benefits is the mentorship program for students, professionals, faculty. If you are a student, we have the Materials Advantage student program. If you're a graduate researcher, we have the Global Graduate Research Network. We have the associate membership. If you are a professional and have never been involved in ACerS, you can join us for free for the first year. And then the second year is only $40. And after that, the individual membership. So this webinar is brought to you by the Cements Division. And who is the Cements Division? It's one of the 11 divisions of the American Ceramic Society. We advance the fundamental material science of cement with an emphasis on nano and microscale research and develop new technologies for concrete. There's opportunities to connect, meeting and event, resource, leadership development opportunities, and award. We also organize our annual meeting, Advancing Cement-Based Materials meeting. And I would like to announce that we're officially open for abstract submission. So if you want to check out one of the past conferences on cementitious materials advancements, this is the one, and it's going to be in June 11 and 13, Colorado. So now I would like to introduce today's speakers. It's Professor Juan Pablo Gevaudan. He's an assistant professor at Penn State and the founder of the Decarb Research Group, which focusing on developing carbon negative cementitious materials to help decarbonize the construction industry. His expertise in CO2 mineralization and concrete material science enables him to create sustainable, durable, and cost-effective construction solutions that turns built environment into a significant carbon sink. Dr. Gevaudan is a Marie Sklodowska-Curie Fellow and has received multiple accolades, including NSF 2026 Idea Machine Finalist Award and recognition from the American Ceramic Society, along with over 20 peer-reviewed publications and patents and in innovative cement technologies. We will also have a Q&A session after the talk, but feel free to submit your question during the presentation in the Q&A box. And we're gonna go through it after the talk. So now I would like to give the floor to Professor Gevaudan. Hey, thank you so much.
Yeah, thank you so much, Allie, for that wonderful introduction. Let me share my screen here.
Yeah, let me stop my idea.
All right. And can I get confirmation that you all seen my screen?
Yes.
Okay, great. Well, thank you so much, everybody, for joining this webinar. And thank you, Allie, for the invitation. I'm very excited to be presenting to you about our research on how we can decarbonize the concrete sector. Now, the title of this presentation is Transforming the Built Environment from a Net Carbon Emitter to a Critical Carbon Sink. And you're thinking, how are we going to do this? How do we do this? So I want to introduce you today our innovations in CO2 sequestering concrete products. Like Ali said, my name is Juan Pablo Gevaudan. Feel free to call me JP. And I am an assistant professor here in Architectural Engineering Department at the Penn State University. So I also, as part of my faculty appointment, I lead the Decarb group, which is composed of 6 researchers, graduate researchers, and 2 R&D engineers. mainly Dr. Anand Nathan, who is our senior R&D engineer, who has helped us with more of the technical implications of our technology, building, fabricating, and so forth. And then Jaden Kumfer, who is our R&D technologist, helping students not only fabricate experimental testing setups, but also running a lot of our innovations that I'm going to be presenting for you today. Now, I would like to highlight here Jonathan Smith, Matthew Hollingham, Dia Brown, Michelle Juan, Yi Xiang, Delaney Link, who are our current graduate researchers and who have made the technologies and the innovations in this presentation possible through their hard work and dedication. Now, as a decarb group, as our research group, we're really interested in these decarbonization goals that we have set that are quite ambitious in the United States. So we want to decarbonize industry by 2050, yet the progress towards that decarbonization has been lagging. Yet we also see that not only do we need to accelerate this decarbonization effort, but we also see that there is an increased resource use intensity in concrete specifically. And I'm going to discuss more about that later on. But as a research group, these two main challenges really motivate our work. So we're always trying to come up with decarbonization solutions that can address not only the carbon economy, but also urgently create opportunities for the circular economy, which are much needed. So the question, if we want to have an overall research question for our research group, is how do CO2 sequestration processes influence the material and environmental performance of carbon-negative cementitious materials? Now, if we want to give an overall hypothesis, we hypothesize that the only way that we can decarbonize the concrete sector is really through looking at the sector through a cradle-to-cradle perspective, where we can think about new feedstocks or new processing technologies and new material technologies that can allow us to sequester more CO2 over the service life of the material itself. So a lot of words there. We're going to unpack all of these in today's presentation. So let's set the stage a little bit more. We know that the concrete sector needs to be decarbonized. And in order to do that, we need to have cost-effective and scalable solutions for CO2 sequestration. When we look at the Global Cement and Concrete Association, the decarbonization plans by 2050, we see that CO2 capture and utilization accounts for 36%, and it's actually the biggest contributor to that decarbonization plan. When we look at the UNEP Global Building Tracker, we see that the decarbonization efforts across industries around the world really are lagging behind. So out of 100 points, we're actually 40 points behind already. So this really means that in order to develop this scalable, innovative, and effective solutions, we really need to be thinking about how CO2 sequestration can be implemented in concrete sector. Now, in order to do that, I'm going to be talking to you about two main ways that our group is trying to achieve this goal or help achieve this goal. And one of them is a material innovation, and the other one is a technological innovation. So our research group mainly focuses on these two different thrusts of research. The first one, the material innovation, we're really looking at carbon-negative cementitious materials. Specifically, we're looking at magnesia-based cements and the chemistries behind those cements, which is fascinating because we think, as a research community, we think that this could be the first carbon-negative cementitious material out there. Particularly, we're trying to solve one of the biggest challenges in those cement chemistries, which is that we have delayed long-term expansion of the magnesia that we use to create them, which creates some really important durability challenges. So we're really interested in advancing our understanding of the magnesia hydration and engineering that hydration process so that we can create these carbon negative materials that will be viable and scalable. Now, I won't be talking about our research on that material innovation. I want to turn the focus to this technological innovation for the carbon sequestering processing technologies. This is our second research thrust. And in this research thrust, our group has developed a new process that uses CO2 to actually improve the performance of cement replacements, fillers, aggregates, while still sequestering CO2. In particular, we're working on understanding the carbonation kinetics and the performance improvements of these CO2 sequestering products. And today I'll be showing you how we do that, why we do it, how it compares to other current technologies, and some of the really exciting results around why it works, right? So before we go there, I just want to highlight a little bit of the challenges that we have right now when we're thinking about decarbonization in general for any industry source point. We're going to focus it a little bit on concrete, but this applies to other industries as well. The first thing is the cost of carbon capture and storage is really high, between $150 per ton of CO2 to even above $350. Most of those costs are coming from capital expenses, which is the amount of money that you need to invest to install the equipment, pipelines, and so forth, as well as operational expenses, which is just operational costs over a whole year. When you're looking at these costs, they're quite high. And for capturing about 100,000 metric tons of CO2 per year in a current technological level carbon capture and storage plant, you'll see that those are above like $70 million with variable operational cost. So the real need behind this challenge is that we need economically viable carbon removal and storage. Just to add to the complexity and the cost of carbon capture and storage is that a lot of these plants actually require multi-year assessments of geologies where we plan to actually store that carbon. We know that cement production, for example, happens near limestone deposits. Yet near limestone deposits, perhaps the cap rock integrity is not sufficient to accommodate also CO2 storage. So this creates not only an economic implication, but also a policy implication behind this challenge. So the need there is effective installation at point of emission, where we may or may not have a geological cap rock to store that CO2. Now, the last two challenges that I want to highlight here are more applied to the concrete sector. We know that industrial emissions are going to increase due to urbanization trends globally. We know that steel, cement, and glass production accounts almost 9% of global CO2 emissions, and that the CO2 emissions for cement, for example, are only going to increase. So we really need to reduce these industrial emissions. When we look at concrete specifically, 30 billion tons of concrete used globally each year also means that concrete is the most resource-intensive material in the world. And we're going to talk a lot more about resource intensity, because when we look at cement, that intensity is only going to increase, and it's going to increase by 50%, the estimates are, by 2050. Yet when we look at cement replacements, such as fly ash, for example, those have continued to decrease over the past 2 decades, which creates a real need for reducing the resource use intensity of concrete or using less cement, which that's mainly what it comes down to sometimes. So the first two challenges is that we need to increase CO2 sequestration capabilities, while the two last challenges here is really we need to decrease cement demand. But how do we do it? So let's focus on the first one. So real quick, this is a map of the contiguous US where you'll see that the light brown areas here are where mafic and ultramafic rock deposits are. And then the green circles are industrial emission point sources, mainly CO2, as well as some other greenhouse gases and other emissions. Now, the larger the circle means that the larger that point source emission. Why mafic and ultramafic rocks? Why am I talking about these? Well, they offer a key benefit, and they can actually mineralize CO2 with some technological advances that I'll describe later. What this means is that CO2 will be turning into a mineral from a gas into a solid, which is really great because then we keep CO2 away from the atmosphere, not contributing to the greenhouse gas effect. Now, another key thing that is really beneficial from basalt is that it's highly abundant, more than 3 million gigatons in the contiguous US. It's near where we're emitting these greenhouse gases, and it can be economically viable. So one of the goals here that we have is how can we advance mineralization of CO2 with basalt that is abundant in the US at the industrial emissions points to provide this economical and viable alternative to carbon capture and storage. Now, when we're looking at decreasing cement use, here, let's look at trap rock. Trap rock turns out to be basalt, and it's actually a basalt that is quarried and used for aggregate. So here you have a few of the quarries for trap rock that we have in the eastern coast of the US. Now, this is a picture of one of these basalt quarries or trap rock quarries. So it turns out we already are mining basalt, and basalt has an ideal cement chemistry composition with more than between 60 and 70% by weight of silica and alumina, which makes it a really good cement replacement. However, it doesn't react. We'll get to that part later on. The location is great because it's near metropolitan areas, and if we can actually turn this basalt into a reactive cement replacement, that will be a great benefit for providing cement replacements to major metropolitan areas in the northeastern US, as I'm picturing here. Now, this is an untapped market. Right now, we import SCMs, particularly in the cases where we're importing from Europe or Southeast Asia. And sometimes those prices can reach exorbitant levels. So the goal that we have when we're thinking about reducing the demand of cement is how can we use basalt to not only mineralize CO2 at a national scale, but also manufacture new domestic, abundant, and viable cement replacements. Now, you may be thinking, wow, that is very ambitious. That is kind of crazy. But our technologies are actually able to do that and have actually been shown to do that. So our innovation is called mechanocarbonation, and it is a critical solution because it allows us to decarbonize industrial emissions in the US by doing two things. The first is an economically viable, low operational energy and effective CO2 mineralization process that uses basalt, trap rock. And then the second is that by doing that, we are actually able to manufacture a domestic cement replacement for the replacement of Portland cement, as well as some other applications that we're investigating, which I will not discuss in today's presentation. So you're thinking, oh, this sounds great, but like, how does it work? What are we actually doing? Let me show you. So with this picture that we just saw, here our senior R&D engineer, Dr. Anand Swathinathan, is pointing to a gas cylinder in the back, which we have retrofitted, and this is our first version of this technology. We're in generation 2 at the moment, so it doesn't look quite like this. But we're able to pump CO2 from the bottom of our steer media tank. What is happening inside that blue tank right there is that we have a steer media reactor, which allows us to mill the basalt rock while we are injecting CO2, mixing both liquid, gas, and solid phase together to actually not only carbonate the calcium and magnesium in basalt, but also break apart the crystal structure so that it can create a cement replacement. Here, I'm listing a couple of variables that are very important in this process, such as our mixing power, the liquid-solid ratio, and bulk-to-powder ratio of the reactor. And I'm going to show you how changing these variables actually changes or affects the performance of not only our CO2 mineralization efficiency, but also the reactivity of that cement replacement. So you're thinking, this sounds great, but what has been done so far? And that's a great question. So far in conventional aqueous carbonation, you're thinking of using an industrial byproduct, hopefully something that is a bit alkaline, that upon some milling, maybe you have some high energy milling, so you're gonna mechanoactivate that industrial byproduct. Then you would take that powder material and put it in a pressurized condition with CO2 to, again, mineralize that CO2 gas into a solid mineral. And then you get this carbonated waste, which has been tested for as a cement replacement and other applications, and it works. However, the milling and the pressurized aqueous carbonation are actually very energy intensive processes, which negate sometimes, oftentimes, the environmental benefits of this process. The other thing that I mentioned here is that it's a limited supply of industrial byproducts. We don't have a lot of them, but that's another question, and we can talk more about that later. Now, in our novel mechanocarbonation process, we're using abundant basaltic rocks, and that is a key part of this innovation. The other part of this innovation is that we actually combine the mechanoactivation and aqueous carbonation into one single process that is more simple and doesn't utilize high pressures, and we can control how much energy we're inputting into that reactor. Therefore, we are maximizing the environmental impact or benefits for this particular technology. Now, the carbonated cement replacement or the carbonated product can be used for cement replacements and support sustainable concrete production, which in the US, we rely on using cement replacements to create low carbon concrete. So it's the main strategy that we have. Excuse me. So what I want to show you is how mechanocarbonation compares to other conventional aqueous carbonation methods. And in general, other aqueous carbonation or just using, looking at the service life of concrete that also absorbs CO2 and sequesters it in a mineral carbonation process as well. What happens in this process is that, well, service life, it only achieves less than 25% by weight of the potential for concrete to absorb CO2 from the atmosphere. And that is due to some diffusion limitations. Yet also wet and milling and wet aqueous carbonation has limitations as well, mainly diffusive barriers that form in these processes and only achieve less than 60%, in some cases a little bit higher, but they're really limited by these diffusion barriers as well. In mechanocombination, because we are milling, we can actually exfoliate these diffusive barriers, which turns out to be a lot of silica gels, and actually achieve up to 100% carbonation efficiency in just about 3 to 12 hours. So we are accelerating the process much, much higher than other technologies here. Now, the research question that we're going to be exploring in this presentation is, what is the SCM performance in carbonation efficiency of doing mechanocarbonation on basaltic rocks? This is the first study that has looked into this particular application. And here I'm excited to show you our first results. Now, these are hot off the press results. So We are tying the knots in a few of these analyses and collecting the last bit of data to finalize these results. And we hope to be publishing them in the next couple of months. So be on the lookout for publication, our first publication on the mechanical carbonation basalt. One thing that I forgot to say, a lot of the mechanical carbonation work so far has been done on metallurgical slags or Portland cement waste, which are alkaline materials and have that benefit to increase the efficiency of mineral carbonation. So I won't be going into details on that, but like if you have questions, just let me know and I can definitely talk more about that. So just to give you an idea, right, of like the experimental setup. The first thing is we are exploring 4 different conditions where 4 different experiments where we are mechanocarbonating this basalt. The chemical composition of the basalt, I want to just point it out here, is in table 1. And what you can see is that we have 5.7, 5.8 almost, right, weight percent of magnesium and about 9% by weight of calcium. That is the 2 main components. Those are the 2 main components that we're trying to carbonate, right? That we're trying to use to convert CO2 gas into a mineral. Now we're going to test the 4 conditions where we're varying 2 different variables in this mechanical carbonation process. So the first one is the milling energy, which is in revolutions per minute or RPM. We have 2 conditions there. So 250 RPM, which turns out to be a low milling energy, and our higher milling energy at 500 revolutions per minute. Now we're also varying how much ball media in the for grinding we have in comparison to the basalt powder. So we have 2 different ball to powder ratios, 10 and 40, right? Testing for mechanical carbonation in this particular study only lasted 3 hours, right? So all the results that we're going to show you are for 3 hours of mechanical carbonation. Now, the first result that I want to show you is how the power is actually changing in the first hour of mechanical carbonation. And what you can see here is that the power in joules per second is actually decreasing as we progress during this mechanical carbonation. The reason why I wanted to show you this first is that this is a really important key takeaway of the technology itself, is that as we mill, we're actually breaking apart the basaltic rock and fluidizing our reactor so that it consumes less power over time. This is really important when we're thinking about life cycle analysis and technical economic analysis to make sure that this technology has the maximum benefit to decarbonizing the concrete sector. Now, the key reaction that we're relying on is this particular reaction where we have calcium oxide or magnesium oxide reacting with carbonic acid to create either calcium carbonate or magnesium carbonate. These are the mineral carbonates that are being formed to lock away our CO2. Now, when we looked at the X-ray diffraction patterns of basalt and then the basalt that has been mechanocarbonated in these conditions, the first thing that we notice is that the diffraction pattern intensity have decreased from the original. Now, I haven't labeled all the different calcium and magnesium rich silicates that are here, but some to note are clinochlor, labradorite, and lizardite that have seen a noticeable decrease in the intensity of their patterns. This means that these calcium and magnesium rich silicates are actually dissolving during mechanical carbonation. And this is actually really beneficial for us because that's what we wanted to do. We want mechanical carbonation to dissolve these silicate minerals such that they liberate calcium and magnesium ions that are capable of reacting with carbonic acid and then creating that carbonate phase, hence mineralizing the CO2. So that's great. But what that also does is that as these silicates dissolve, the silica that is dissolving is going to go through a polymerization and gelation process, which really just means that that silica is going to agglomerate and create a gel that we hypothesize and we show can be positronic. So before we get there, let's look at how much CO2 are we actually carbonating and sequestering as a mineral. So to do that, we actually first wanted to compare it with some of the traditional carbonation methods that we have out there. So in the figure 3 that you're seeing here, I want you to pay attention to the black and white boxes shown there. And both of these is the original basalt without any process to it. And then the black one is basalt that we have carbonated in a carbonation chamber. This is one of the bread and butter sort of techniques for carbonation in the cement and concrete research field. You can see that there is no appreciable difference between both of them, meaning that carbonation in a carbonation chamber does not really do anything to carbonate the basalt. And that makes sense because we need mineral dissolution to actually induce carbonation, which is exactly what the green curves show you. And particularly what they're showing you is that ball to powder ratio turns out to be a key variable here, controlling how much carbonates can we form in mechanical carbonation. And turns out that we form about 2.5 weight% of carbonates in basalt in just 3 hours, which really marks an opportunity in our technology to not only can we carbonate, but we can actually improve the efficiency of carbonation if we change and control the variables that I mentioned before: milling energy, ball to powder ratio, liquid to solid ratio. Side note here is that the liquid to solid ratio has been fixed here to 10. So keep that in mind. Now, when we're looking at cement replacement performance, ASTM C1897, or the R3 test, is really one of the key testing techniques that we have to really understand whether a material is going to be reactive or not. In other words, is to test whether a material could be used as a cement replacement, or is it going to be just an inert filler. What we see is that in the results here in figure 4, when we compare it to basalt, plain basalt without any mechanical carbonation, we see that at 40 ball to powder ratios, we actually increase the reactivity by almost 5-fold. And this is one of the most exciting results that we have, is that not only can we carbonate these materials and sequester some CO2, but we can also in that process improve the reactivity such that we can create domestic cement replacements. So this is really exciting. Now, the light blue and light pink curves here, those are for ball to powder ratios of 10, and you can see how that reactivity is much lower, but you see an increase in reactivity as well, nonetheless. So again, this really shows that our technologies can be modified and can be improved upon further engineering. But in order to do that, we really need to start looking at the microstructure and really understanding the mechanisms. And this is where we have been spending a lot of time in the lab, looking at how these mechanisms actually differ when we start to change a lot of these variables. So here is an SEM picture of just basalt. This is just a plain basalt particle. When we do mechanical carbonation on basalt and at a 10 to ball to powder ratio and just increasing that milling energy, what you can see is that the surfaces are quite disrupted. And interestingly, we have aggregation of these smaller particles or clusters around the surface of this basalt. We have really interesting hypotheses for why this is happening. And we have indications to believe that this is actually amorphous silica gel clustered with carbonates, sorry, and they are why we not only have the carbonates that we see in the TGA, but also that increased reactivity in that SEM. Now, when we look at 40 ball to powder ratio, this is our highest reactivity SEM that we can produce from basalt. We see that not only are these, yes, we're decreasing the particle size of basalt, but we can see that you still have those clusters forming with large disruptions to that surface morphology of that particle. Because we were really interested in this cluster formation, we wanted to run particle size analysis of the mechanocarbonated basalt. And for 40 ball to powder ratio, we see that we have really large agglomerates that are forming near 1,000 microns. This is fascinating because a big concern that we have in the cement and concrete field is that if we are milling, we are going to actually increase water demand for these cement replacements. So one key thing here is controlling the amount of surface area that we're generating through milling, which this agglomeration and clustering may be beneficial for us to control that water demand. Now, we're looking at those investigations further to really tease out how workability and water demand can be affected. Interestingly enough, when we're looking at that 10 ball to powder ratio, in both cases of 500 RPM or 250 RPM, we see that agglomeration still occurs, but the agglomerates are not as big as when we have that high ball to powder ratio. Another key consideration here that I meant to highlight in previous results is that milling energy, how fast we're spinning our rotor in that reactor, signified by the revolutions per minute here, 500 or 250 RPM, really shows that there is no real difference in either the reactivity or the carbonation. This is really exciting for us because it shows that we could potentially use lower speeds in how we're milling our materials, but still achieve carbonation and SEM reactivity metrics or goals. That is, again, exciting because we can lower that operational energy that we need to manufacture these SEMs. So more results on that, hopefully in the next couple of months to share with all of you. And I wanted to conclude, I don't know how, don't want to run over here, but I just wanted to conclude with some of our key observations. So we started out with the key question of what is the SEM performance and carbonation efficiency of these abundant basalt rocks after mechano-carbonation. And really our hypothesis was that we needed to increase both ball to powder ratios and milling energy, basically hit it with everything that we have to achieve these two metrics. What we found is that the milling energy doesn't really matter as much. It doesn't have such a big significant influence into our results. And that, yes, we can actually carbonate these basalts, achieving 2.5 weight% of CO2 uptake and achieving more than a fourfold increase in reactivity, making these mechanocarbonated basalt materials a good option for cement replacement. And very interestingly, these aggregated clusters from SEM images show that these clusters could have a really important role to play in the mechanisms by which this mechanical carbonation is happening, and that the formation of silica and carbonates is interlinked. And we're exploring that mechanism a lot more in our investigations currently. But we hope to be publishing these in the next couple of months to share with everybody and really understand the mechanism so we can engineer this process for improved efficiency and large scale deployment here in the US. All right, so with that, I think we can open it up for questions.
Yeah, thank you so much. JP, it was a great talk. Just before actually we go to the Q&A session, I would like to invite you everyone for our next webinar. Just do a quick marketing. So on February 24, we will have a talk from Agnieszka Jędrzejewska, associate professor at the Department of Structural Engineer at Silesian University of Technology, Gliwice, Poland. And she will give like a great talk on the hydration-induced cracking of reinforced concrete structures, a European perspective. It will be a great talk, so I invite everyone to register. We're going to send an email probably today, inviting like everyone. Yeah. Oh, sorry, I didn't like share, but anyway, yeah, that's what I was like saying. So yeah, now we can go to the Q&A talk. We have a few questions already here. So the first question is from Acton Char. Is there any heating in the reactor in this mechanical carbonation process?
It's a great question. So there is no active heating, but we actually actively cool the reactor because we want to maintain constant temperature of ambient constant temperature around 25 degrees Celsius. But you can imagine that the friction that is happening in the ball media for grinding or what we call comminution is going to actually have a lot of frictional forces that are going to increase the temperature within your reactor. So that's what we need to actually actively cool. But one of the things that we've been discussing is actually removing the active cooling, because in mineral carbonation, we're actually trying to accelerate the kinetics of that reaction. So by allowing it to heat up, although we're not precisely controlling it, we can actually increase the reaction kinetics and also, therefore, hopefully, increase the carbonation efficiency as well.
Another question is from, have you investigated the size of the ball mill in the mill or the composition of those balls, aluminum oxide versus silica?
Yeah, that's a great question. Yeah, so that's the that is one of the fourth levers that we can pull. As engineers, we like levers that we can pull and you know, in the terms of optimization. So we haven't yet, but it's in our radar to actually not only go in terms of like different sizes of balls, but actually increase the tensile forces that are happening in the reactor as these forces fracture the particles. And the way that we can do that is by changing like the geometry of the milling media. So there's a lot of different things that we can look at. We're actually working on discrete element method modeling to actually model how this happens in a computational simulation, but then also how it would happen in real life. That will be our benchmark experiment, right? Now, the balls that we have a couple. We do have corundum, which is their aluminum ball media. So yes, that's the main one, but they sell all their ones. We have some stainless steel as well.
Okay, there is another question from Jose Paul. Is figure 4 y-axis normalized to mass of SEM or perhaps the net cumulative heat?
So yeah, I believe that is the cumulative heat for the reactivity. But it is normalized by mass, so it's joules per gram.
And which is the pressure of the reactor during mechanocarbonation?
Great. Okay, so that is one thing that differentiates us from a lot of the work that is out there. There's only two other research groups around the world that have similar mechanocarbonation processes, although they rely on high pressures up to 150 bar. Our reactor actually is 9 psi over ambient pressure, which is very, very low pressures near ambient, which allows us to actually have a scalable and deployable technology. And it's one of the things that we're very proud about in our technology.
Cool. And if you do mechanochemical grinding first and do the carbonation after, what do you think will be the carbonation efficiency? Decrease, increase, or similar?
Oh, I love this question. Okay. So we're gonna disregard the energy implications of that, but in theory, what mechanochemical grinding is doing is that it's breaking your crystal structure apart so that when you do any aqueous carbonation or mechanocarbonation, that you can liberate a lot more of those calcium or magnesium ions that you want to then mineralize into carbonates. So it would increase, if anything. Now, the hardness of the mineral is really important here, as well as its crystal chemistry and structure. So, we have to think about which mineral we're thinking about here. But if it's basalt, for example, yes, it would definitely increase as well. So in majority, that would increase for other silicates as well.
And did you confirm the capture carbon using techniques other than TGA? I ask because the mass loss around 600 T in TGA does not always correspond to carbonates. Additionally, I did not observe peaks corresponding to calcium or magnesium carbonates in the XRD profile of mechanocarbonated basalt. I will recommend the use of technique like total carbon analysis to confirm the actual increase in carbon after mechanocarbonation.
This is an excellent question. Yes. So we're in the process of doing total carbon analysis just to verify the TGA results that we have. Now we are doing some other analysis that is looking at the aqueous composition of the solution as we're mechanocarbonating basalt and other silicates like olivine. What we're finding out is that by mechanocarbonating, we're actually affecting how the nucleated growth of carbonates and silicates, so that's the silicate gels that I have been discussing, is happening. So what's really, really interesting is that we may not really have well crystallized carbonates. And that's really, really interesting for us. We're really probing, we're very excited about that science and that discussion around there, because it's really looking at non-classical crystallization of carbonates. And yeah, we're excited to have hopefully a couple of projects on that topic. So yeah.
We have another question for Gary Smith. Hey, Gary, are the gels that form on the modified surface crystalline or amorphous? I didn't see any broadening in the XRD pattern.
Yeah, so the silicate gels are amorphous. The XRD patterns have an amorphous hump around 22 theta degrees. So that's where we see there is some peak broadening. It's not significant, although peak broadening can really be due to the nanocrystalline sizes of those particular crystals that are in that diffraction intensity. But the amorphous gels wouldn't be part of that peak broadening. It would be mainly represented in that amorphous hump around 22 theta. Now, the peak of that amorphous hump kind of shifts, and there's a lot of amorphous XRD research looking at maybe compositional changes that can shift that peak of the amorphous hump. But it's inconclusive at the moment. But yeah, that's what it would be.
Mm-hmm. I have another question. Can the same performance be achieved continuous rather than batch?
Yeah, so excellent question. We haven't modified our reactors to have a continual feed. Therefore, it's not a continuous reactor. But yeah, I don't see why not. It would be one of the main key advantages of our technology is that we're also allowing for well mixing of the CO2 with the basalt and the granite media so that we can break the crystal structure and allow for carbonation to occur. So in a continuous reactor, this could still be achieved, but there's a lot of geometrical considerations and orientations that need to be thought of. But in theory, yes, we could do that.
Mm-hmm. And how would this basalt mineralization be used in concrete application? I did not understand the actual application except the carbonation.
How would it? Okay, wait. Okay. Let me think about this one. I didn't understand the actual application except decarbonization. Okay. Well, yes, we start with decarbonization, right? Because we're using basalt in mechanical carbonation reactors, right? But the product, right? That's what we can give to our concrete sector to use as a cement replacement. So not only are we taking the CO2 emissions from the concrete sector and using those to mineralize it into basalt, but then the carbonated basalt we can give back as a cement replacement to our industry. So it's a twofold benefit here: decrease in CO2 emissions, but then also using those to create cement replacement that we're running out of in the US because we don't have a lot of fly ash anymore.
Mm-hmm. Yeah, we have a lot of questions. Oh my gosh. Juice from Giuseppe Behara. Did you try to run conventional aqueous carbonation without milling on the same material with equal size? If yes, which is the carbonation degree compared to mechanical carbonation?
Awesome question. Yes. So that is an important control, right? So yes, we are running that experiment right now, actually. So that is one of the main experiments that we need in order to benchmark our results. But from the initial findings that we're looking at, the carbonation is less than 1% in those cases.
Mm-hmm. And basalt mineral composition can vary significantly depending on the geographic location. Is there a specific mineral that is more favorable for this process?
Yes. So we want to have basalts with a lot of olivine. So we want high olivine content. That is one of the main silicates that we can use for mineral carbonation. So, yeah.
Mm-hmm. And do you think changing silicate and calcium ratio, there will be a high CO2 uptake?
I'm assuming changing the silicon to calcium ratio in the basalt. So if we decrease the silicon to calcium ratio, and depending on where that silicon calcium ratio lives and what kind of silicate are we talking about, yes, we could have higher CO2 uptakes. But these questions on silica chemistry or the crystal chemistry of that mineral are really important, and they require more research.
Certainly, you cited the reduction of XRD peak intensity as evidence of mineral dissolution in basalt. Did you consider this being the effect of morphization due to high energy grinding rather than their dissolution?
Yeah, this is a great question. So amorphization just means that you're breaking the silica atomic environment. For example, you're going from a Q4 as like tectosilicates have it, right? Like quartz to maybe a Q3. So in essence, dissolution is part of that process where you're breaking and continue to break that structure in order to increase the aqueous concentration of that silica. So yes, you're absolutely right. It could be part of the breaking of the crystal structure, but from our when they didn't show some of our aqueous concentration results here, but yes, we see that also is increasing that silica concentration in our aqueous solution.
And was the formation of silica gel investigated by NMR F-D or spectroscopy? Silicates in basalt are generally crystalline, so how much of it is amorphosized by mechanocarbonation?
So excellent question. So we tried to run NMR. However, the high iron content in our basalts render that analysis unfortunately not as helpful. FDR is a great suggestion though. So that's something that would be interesting to see the different environment bonding that we have. Unfortunately, it may not really tell us where we have silica gels unless we're like mapping. But that will be a great addition to our mechanistic studies of this mechanocarbonation process. Thanks.
Okay. Okay, so we're almost like up on time, but I still have like 3 questions. Are you okay if we're solving all those 3 questions?
Sure.
Yeah, okay. Are you planning on testing the longer-term stability of the last crystalline carbonate phases that are predicted, which is important for carbon dioxide removal and storage?
Yes, absolutely. That's a great question. So yes, that is one of the projects that we're hoping to kick off here in the next year, hopefully, because it's really important that we understand that.
Do you think thermal activation prior to carbonation can be better or less effective than mechanical chemical carbonation for basalt? Why or why not?
It's hard to tell, mainly because we haven't studied it, so I don't know. But thermal activation could be helpful. Again, one of the main goals in this research is to utilize processes that are not going to add more energy or require more energy for us to accomplish the same goal. So we really are trying to have low energy processes that can maximize the benefit of CO2 sequestration.
Mm-hmm. And do you think if you keep increasing the grinding, making the materials completely amorphous, there will continue increasing carbonation? Meaning, does the amorphous and carbonation relationship is linear?
Ooh, that is a great question. Is it linear? I'm not sure. I suspect that it probably isn't, due to just the nature of how the silica gels are forming, which I suspect are forming near the surface. And as we exfoliate, we're sort of creating those clusters that I showed. So more on that, hopefully, in the next couple of papers that we publish. That is an interesting question. We don't know yet. We don't know yet.
Okay, we got like 2 more questions. Are you okay after those? Yeah. Okay, sorry. Mechanocarbonation, both high energy grinding as well pressurized CO2, making it energy intensive. So those 2.5% CO2 uptake outside the costs and energy associated?
That's the thing. Our process does not use high pressures, and it does not use high energy grinding as showcased by the milling energy at 250 RPM. We show that at 250 RPM, fall to power ratio of 40, we can actually still achieve that 2.5 CO2 weight percent CO2 uptake, but also increase the reactivity to similar levels as a high energy grinding process at 500 RPM. So we are running cost and techno-economic analysis to look at cost and energy associated with the process. And the main thing that we have found is that the CO2, if it's coming from an industrial emission, direct point source, and if the energy that we are using is coming from a renewable source, we actually achieve carbon negativity.
Mm-hmm. And how much is the capacity of your reactor? And do you control pH during the process?
Oh, great. Okay, that's another project that we have. pH is really, really important for this process. So controlling pH is not as simple as what one may expect. So we're thinking about a couple of different strategies to understand the effect of pH and engineer it as well. So the capacity of our reactor is about 2.5 liters, and we can produce 1 kilogram of basaltic SCM per 3 hours. So that's our production rate.
Okay, cool. I do have like one question. So yeah, we're done with the Q&A here. So have you looked into like trying using grinding aids during this mechanical carbonation process? I know that there's like some agglomerations, as you said, but like using grinding aid might actually reduce the energy that you're losing, that making it even more efficient or something like that.
Yeah.
Yeah.
No, that is a great idea. We haven't just yet. We've been looking at. We do have a project on the optimization components, looking at techno-economic analysis and life cycle analysis of the technology, because we aim to commercialize the technology or at our current reactor generation. But you know, the main bulk of our work, being a scientist, is really looking at that mechanism and how we can really understand the mechanism so that we can engineer the process for better efficiencies.
Yeah, amazing. Thank you so much, JP, for your talk. It was really great. I think like the audience is also like really happy from like how much people came in and how many questions we got here. I would like to thank you so much for being here. And yeah, and just like a quick reminder, everyone. So we are going to have yeah, I already said in the beginning, but just to remind you to submit your abstract by February 28th for the 15 Advancing Cement-Based Materials. That will be in June 11 and 13 in Colorado. It'll be a great conference. Yeah, so I hope like to see everyone like there. So thank you so much. Yeah, and I think that's it. Thank you.
Okay. Thank you
Do
so
you have
much.
anything to say? Yeah. Okay.
No, and I hope to see everybody at Cement's ACerS Cement Division this summer. So thank you for coming.
Thank you.